let's look at the root test fairly quickly and just do one example. So we want to go back to the geometric series. That was the key to the ratio test. And the terms of the geometric series, a r to the k, and one way to extract that r, when the geometric series, to tell whether that's convergent, you just need to know if that ratio is between -1 and 1, if it's a small number. And one way to extract for the exact geometric series, to extract the ratio, is of course to take the ratio of successive terms. That's why it's called R. But there's another operation you could do on the geometric series. If I just give you the list of numbers, and I don't even tell you necessarily for sure it's geometric, where you could extract that magic R, which is so important. And that's going to turn into a general test for an arbitrary series, which is the root test. So what we're going to do is, if you want to extract the r here, it's been raised to a k power. So you basically take the kth root of it. Okay, so let's limit k goes to infinity of the kth root of that, or sometimes it's nice to write that as a fractional power. Okay, now let's see. If r is negative, you get some weird issues about square roots of squares, things like that. And we really just want the size of the ratio. So you know what? Let's just take the absolute value there. Get rid of all those issues. Okay, so that's going to be absolute value. And as soon as we do that, we want to think, oh, we're really testing for absolute convergence, or this is leading to a test for absolute convergence. And that's exactly right, just like the ratio test. Okay, let's see what happens. We get absolute value of a to the 1 over k. So higher and higher roots of a constant number times r to the k to the 1 over k. Well, absolute value, so you just get absolute value of r. Okay. And here's just a little fact about roots. I think we know this already, that if you take a constant number like 2 or 10 or even 1,000, and you take the square root, cube root, fourth root up to the millionth root, that goes to 1. And so you just get the size of the ratio. So far this is just an interesting fact about the geometric series, but it does suggest, well, if I do this to a geometric series, and I don't even really, maybe I'm not sure at the start that it is geometric, I just do this geometric series, when this number is less than 1, it will be a convergent geometric series. When it's greater than 1, it will be a divergent geometric series. Okay, so that suggests, it doesn't prove, but it definitely suggests something that is really true. We just take an arbitrary series, some a sub k, okay, and it's essentially a kind of a clever comparison to the geometric series. Let's take the absolute value of those terms, and the kth term, we'll take the kth root of it, or in other words, raised to the 1 over k power. And then we'll see what number we get. Okay. Now, there's some cases where we wouldn't even get a limit, and that's going to be one of the cases where this is inconclusive, although you can be cleverer about it with a more advanced version of the root test. Okay. But the claim is that if, let's call that L, if L is less than 1, then basically we've detected that the rate at which these AKs are getting small is very similar to a geometric series with this ratio, and that's a good ratio. Then the sum converges. And it converges absolutely. Because this is a test that just throws away that sign information at the start, is just a test for absolute convergence. But if the answer is yes, that's great, because it converges in all ways you want. And if L is greater than 1, then it diverges, because it's looking a whole lot like a divergent geometric series. Another way to say this is, our usual rule is, if I've got any kind of series, we're asking, do the terms get small fast enough? And what we're doing is we are looking at terms that are getting small, and then we're taking kth roots. Those tend to push things towards 1. It takes a small number and pushes it towards 1. So we're making it harder for it to go to 0, and harder to get small. And it turns out, if that's kind of a standoff with L less than 1, then it turns out, like I've said, it's like a convergent geometric series, and it's going to converge. If it's greater than 1, it turns out these weren't getting small fast enough after all. So let's just do one example. So one thing about the root test, for the kinds of examples that we see in kind of first-year calculus class, we have to contrive them a little bit to get explicit answers. And so I remember when the first time I learned about the root test, I thought, this isn't such hot stuff. Seems like the ratio test is better and various other tests. Turns out the root test, especially for power series, and especially for sort of the theory of power series, it's really powerful. It has some nice theoretical sort of general aspects. But for calculations, it is something where it works on sort of fairly specific examples. So let me give you one of those fairly specific examples. It's very similar to a problem in the book, but a little bit different. So let's look at this guy. Let's first sort of analyze it first. That, if it was just sum of 1 over 1 minus n, that'd be like, you know, 1/2, 2/3, 3/4, 4/5, that kind of thing. That's not even going to 0. But if I take some numbers that are less than 1, and then take big powers of them, those are going to be pretty small numbers. Now, are they small enough? These guys are getting close to 1. Then I take the power, that's probably going to be close to 0, but again, it's really about whether it's going to 0 fast enough. Okay, so there we have our a sub n. Oh, and I changed from k to n. Since I like k, I'm going to put in k. Okay, so a sub k is just the term here. And so we're going to take L. That's the limit. K goes to infinity. And you can use n here totally. It's just I like to reserve n for when I have like a partial sum. And that in the end of the partial sum. So, and we're going to take that to the 1 over k power. Okay, so the absolute values don't do anything here. This is always going to be a non-negative number, and so the absolute values don't really change anything. Kind of bad style to do it in place, but I'll do it like that, just be a little faster. And now something really nice happens. I've got something to an overall power, and this is where the root test is highly indicated. It's some complicated expression, but the outer level of it is some power that depends on k. And so I've got the rule is that these exponents multiply. And I get a k. Hey, that is a very, very famous limit. So it's very nice to remember when you're doing things with interesting bases and exponents that are both variable, that we have some results on this. Now, if this were totally random, we might need to do a L'Hopital, and the kind of L'Hopital where we do a log first. But this is actually a famous example. We should remember that the limit is k goes to infinity of 1 plus x over k to the k. That is e to the x. That is an alternate definition of e to the x. Here, that x is minus 1. I get e to the minus 1. Aha, that is less than 1. It's about, 1/3-ish, 37%, something like that. And so that says our L is less than 1. So the sum of these a sub k's converges. And if you look at it, as you go out, if you take it up to k equals 10, 100, 1,000, it's really going to look very much like a geometric series with this ratio. I won't, give you shower a lot of numbers on you, but it's really going to look a lot like this geometric series, and that makes sense that it's going to converge because this is a perfectly nice geometric series with ratio less than 1.